Netcasts you love.
From people you trust.
This is TWiT.
Bandwidth for TWiT specials is provided by Cachefly at CACHEFLY.com. This is TWiT special number 126, Democratizing Creation. This is actually kind of cool. You may have seen the Solve for X speech that Omri gave. That was a few months ago, right?
Yeah, in February.
In February for the Google Solve for X conference. Had some really interesting stuff. What were you talking about? What was your talk about?
So I was talking about the software we are developing, Genome Compiler.
Which just shipped 2 days ago.
2 days ago. Go to genomecompiler.com and download it. It's
Well, wait a minute now. Is this like GCC for genomes? What does a genome compiler do?
Well, just like software development, people in software, what computer understands are binary, ones and zero. But people that write software doesn't like type ones and zero all the time.
I'm going to plug this in, and we'll be able to see your screen if you have stuff on your screen that you want to show.
Software tools to design, debug, and compile their code into executables. So people in biology need the same tools to design their code, ATGC, the code of DNA, the code of life, into executables, into new living things. So from
so then the output of that is what? Just
the output is DNA that companies like Austen's and other companies.
So that's where Austen comes in, because you've got to do something with the output of the compiler. Are we going to build? What are we going to build? Godzilla? What are we going to build with this stuff, Austen?
Eventually, yes. That's the long-term goal.
So right now,
I knew you scientists were going to screw it up for the rest of us.
So right now, it's viruses and bacteria.
Does that seem like a good idea?
Oh yeah. So what are we trying to tackle? The huge problem that we are trying to tackle is, we live in a world where we use,
Can you see his screen?
No.
We use.
Let me just check here on the video settings on your screen and make sure it's a 1080i, so that way we can see.
Wow, I get personal
computer
help
from the tech guy. Huh? Yeah. That just means I'm going to screw your computer up faster. That's all.
That's great.
I think we're probably in mirroring is the problem. Not in mirroring is the problem. Can you see his screen now?
I'm not. It's in 57, 56. Can you see what's going on?
I'll get it. It's the same one I was using. No, it wasn't at 1080i. Let's try it.
57.
It's 57, and it is now at 1080i. Should be able to see it.
Yep, just came up.
Okay.
Right.
So here's the problem.
So the huge problem we are trying to solve is that we live in an unsustainable world. We use finite resources of coal, oil, and natural gas to produce almost everything around us. Not just energy and fuel, but almost everything that you see. And that's a huge problem, and living things can solve this problem. Living things has been around.
We didn't do anything. Why would you have lost it? Sorry.
Yeah, sure. So it's not that I have to run the deck, I can just
Well, you don't have to, but I think it's nice to have the deck. Is this the same talk you gave at Solve for X?
Well,
roughly.
It's better looking now.
Switched over again. Why would it do that? Maybe I have to say yes.
Yes.
Do I have to hit yes?
You see?
Yeah. You're right. Confirm.
Oh,
See, he's smart. He knows. He knows. So we live in a world of non-renewable resources.
Yeah, and if you think about it, living things have been around the world for billions of years because they are the essence of sustainability. They can use renewable resources like sugar, sunlight, CO2, and they can produce everything we get from fossil fuels. And the best thing about them is that they can scale. So if you design them just the right way, just feed them some sugar, and they will grow. They are the first exponential technology. They can scale to meet our global challenges. And we can design them because, again, biology is just information technology. So if you look at computers understand binary code, ones and zero.
Lower thirds, John.
So computer understand binary code, but people in computer science doesn't, just sit around typing ones and zeros. They use software to design, debug, and compile their code into executable that runs on computers. And biology is very similar. Biology understand ATGC. You know, that's a binary code of biology.
That's a code, right?
And the executables are chromosome genomes that you know, runs inside of cells, and cells are just biological computers.
That makes sense.
And what we need and what we don't have is what we call a genome compiler, the same tools that we have in software to design, debug, and compile the living code. And we think it's important because, you know, those
That's
tools
really
will
interesting.
enable the design and creation of useful living things we need to solve our global challenges.
Wow.
So this is what we are doing, and we can do it today because the price of both reading DNA and writing DNA, the underlying technologies, has been going down faster than Moore's law, much faster than Moore's law.
Really?
So I think Austen can talk about writing DNA, but reading DNA has been going down from $3 billion to read the human genome to $1,000 today.
Wow.
So we have database exploding with genetic information, you know, that nature designed.
Yeah.
And now writing DNA, that's the cool technology, because you can take this data from different databases, put it together, design it with our software tool, press print, and Austen will deliver the DNA.
Is it kind of an assembly process where you take bits and pieces, or you're not typing, you know, G, T, A, C, G, T, A, C?
Actually, you do. So you can send a text file to a DNA synthesis company, and they'll get the DNA back to you, or in the vial, or they'll take the DNA and put it in a paper and ship it overseas as a document because it's Word on paper. Then you can take that document, put some water, the DNA will get out of the paper, and you can use it to transform living things. So they actually do it today.
What kind of safeguards, though? I mean, I'm worried about bugs.
Literally.
I mean, literally.
Yeah. I'm worried about script kiddies that would load Ebola and print it out.
Exactly.
Yeah. But, you know, nature created Ebola. And one of the most exciting uses of synthetic biology is to develop vaccines faster, you know, develop the cures that you need.
Yeah.
You know, so we need this technology. This technology is here, you know, if you want it or not. We need to develop it.
You're saying nature's already doing it.
The people who develop, you know, bad bacteria are doctors giving antibiotics.
Right.
They are developing, you know, antibiotic resistant.
Yeah, they're
bacteria,
evolving
right?
bacteria to be any
so we need this technology.
Wow.
And this technology is here to stay, so we need to develop it, you know, in the light where we can control it.
So you actually released 2 days ago the first iteration of the gene compiler.
Yeah, you can go to genomecompile.com and install it on Macs and PC.
What would somebody obviously it's a microbiologist that would use this, or?
The first customers are people in labs, like my lab at Stanford, or you know, undergraduate postdocs and the such. But there is a new movement of do-it-yourself biologists. Here in the Bay Area,
so scared.
Here in the Bay Area, BioCurious has a community lab where you can pay small amount of money and do experiments yourself.
You mean the makers? The makers have now moved to
biology. You can
cellular
hack
biology.
Why not? No, it's just
Holy
software.
cow!
Well,
what are you making, Austen? Now, what does this do? How does your thing work?
The primary problem that everything Omri is talking about is up until this point, each letter, each A, T, C, and G has cost about $1 each.
Wow!
So
it is expensive.
Very expensive. So if you're
is this sequencing when you sequencing is analyzing it.
Sequence is reading.
Reading.
Synthesis is writing.
Synthesis is writing.
writing.
Okay.
So you're writing DNA. So to write a virus, you're going to pay over $10,000. To write a genome of a bacteria, you're going to pay over $1 million.
Wow.
To write a human being, you're going to pay about $2.5 billion.
Right. So
now it's too expensive to write entire organisms.
So you're making the maker bot of genomes.
Right. So in Omri, you wouldn't want to write, you know, software code in ones and zeros.
Right.
You'd want a level of abstraction.
Right.
So Omri's software allows that abstraction layer so that you don't have to get into, you know, typing out ATs.
You don't literally type.
No.
Right.
Yeah.
So he adds an abstraction layer to that. So
what does it look like? What does the code look like?
Well, the code itself, you can see. So this is our software. If you can pull
this is
it up.
We're in the genome compiler right now.
Yeah. So right now, so you can, as you can see, you can browse through different genomes or vectors.
So you'll take pieces of...
No, the whole genome. So I can go through viruses, for example. Just this is a bacteriophage. Just drag it here. So this is the whole genome. So you can just...
That's the whole. That's it.
That's a whole genome. It's just 40,000 letters. That's it. Each of these squares is a different gene.
And that's what we call abstraction.
That's abstraction. You can abstract it further away. This is the virus, right?
Yeah.
And you can just rename it. So let me call it my virus.
Okay.
Just save it.
Omri's virus.
Now you can zoom in to the level of abstraction from the genes. Here you see
and so now you might want to change a few sequences.
Yeah, exactly. And to the amino acid, that's a different amino acid that they create the different protein. That's genetic
so
code.
you're drilling down deeper and deeper and deeper.
Yeah, so you can change the genetic code that easily. And then you can zoom all the way into the DNA. And that's the source code.
And this is the ones and zeros.
And this is the ones and zeros. And you can just go around the DNA and you can, start moving.
So you can operate at that low level, but you can do a macro that's higher level.
And you can start moving things around, right?
Oh my God.
You can start copying and pasting, adding more sequence. You can look for whatever sequence that you want.
Cow.
And you can just find it and make a new annotation. Just say, this part, this is not a gene. This is, let's say, a promoter, right? And when you abstract up, you'll see the promoter.
Do we understand well enough the mechanisms, though, of biology to actually productively be able to make these modifications and know what we're going to get?
That's a good question. So we can design to a point, and then what we need to do is, because we don't understand all of biology, it's not...
it's pretty complex.
It's very complex, and there's a lot of black boxes we don't understand.
Right.
So you design to a point, and then you do a lot of libraries, you do a lot of mutation.
Trial and error.
A lot of trials.
And Austen's tool would help with that.
Think about it if you're using a computer. Every time you type a keystroke, you're taking up about, 8 bits or something of memory or something like that. That costs $8 in biology language. So you wouldn't actually program much. You wouldn't write in Word much if it cost you $8
You'd
every
think
for every
a long
keystroke.
time before you typed.
So what happens is that we've developed these amazing computational tools for designing not only individual proteins but also larger pathways. The problem is that we can't afford to execute more than one.
Right.
It'll take about 2 months to make the construct, and then we'll wait a long time to get results on that. I mean, you can't just print.
So what's different about what you're doing, Austen? I mean, Austen's company is called Cambrian Genomics. Are you named after the Cambrian era, the Cambrian explosion?
Yeah, right, exactly. Yeah. So what we're doing is we're leveraging actually the radical change in DNA sequencing technology. It used to cost $1 per letter for reading. So a human genome cost over $1 billion.
Right.
Now a human genome costs about $1,000. And the reason it was able to become so cheap is because it went from doing it one at a time to becoming massively parallel.
Right.
Now think about making the transistors on a computer one at a time.
Right.
It'd be pretty expensive, but there's billions in there, and they cost basically nothing. And DNA itself is actually more simple than those very complex transistors in that computer, and there's no reason they can't be made more cheaply.
So your device, does it do a simulation? Does it actually make the...
It actually makes DNA, and the way that it makes DNA is it uses the massively parallel nature of next-generation sequencing and recovers sequences using a laser from a next-generation sequencer.
It's like a laser printer for DNA.
Exactly.
And is it working?
Yes.
Oh, I'm scared to death.
We've.
So what's to keep somebody from maliciously creating something dangerous?
Well, there is best practices. So the Obama administration, after Craig Venter synthesized the first genome of a bacteria and put it up, so we actually have a living thing that has, for example, an internet address inside of it, because he could just write in DNA. So the Obama administration did a biosecurity committee, and we have a very clear guidance from the CDC. Every sequence that you need to synthesize have to go through a CDC website database to prevent from ordering malicious sequences. And the good thing about biology is you can't really encrypt it. If you try to change a sequence to avoid detection, you will change the function, so it won't work.
The other thing
Are you worried about accidental?
Well, the way this is managed is that this isn't something. This is as a service. People aren't actually taking these machines into their houses, and because
right, exactly.
Yeah.
If the Moore's law starts to apply, this stuff's going to get so cheap that it might proliferate.
I
mean, isn't that kind of what you want?
If you're going to buy dynamite, or
that's true.
You're going to have to get a license.
Right.
But at this point, I think it's going to be as a service, because this is high.
But you chose this name Cambrian for a reason, because you see this as an explosion. This is something significant happens.
People
here.
a lot of times get
something
upset
changes
about.
Big time.
People get upset nowadays about extinction of animals, which I think is really silly.
We just make new ones.
We're going to make new ones, and we're going to make more creatures. Every time you actually press compile on Omri's program, you're making a new creature, a new species.
Right.
and we're going to make
literally making a new species.
We're literally going to make more species within the next 10 or 20 years than have been created by God.
So I won't focus on the scary negative, but although that leaps to mind.
Yeah,
but because we've all seen a lot of science fiction. But let's talk about the positive things. Could you, for instance, make organs this way? Could you?
Not organs. So
not organs.
Where we start right now is there are companies right now trying to develop a bacteria that will produce biofuels, for example.
A bacteria that would generate fuel instead of methane or whatever.
Exactly. That will produce pharmaceuticals, that will produce fertilizers, that will produce plastics, almost everything you get.
What you do is you take an existing bacterium that's close and you modify it.
Yeah, synthetic biology is just genetic engineering on steroid. So it's the technology has been around for, I think, 30, 40 years to do genetic manipulation, and even
it
if
just
you
has been too expensive and complicated.
It's too expensive.
Yeah, but even if you look at the human history, we've been breeding animals for a long time. When people talk about organic,
sure, it just takes a long time to do it.
Yeah, and we didn't actually design it. We just breed and select it.
That's Mendelian kind of.
But now again, this is just software, and you can take this software, this data from anywhere you want, put it together, and press print. That's the.
What's the problem? Oh, you want the website? Yeah.
It's CambrianGenomics.com.
Cambrian, C-A-M-B-R-I-A-N. Actually, you should be able to do this. Cambrian.
Yeah.
Genomics.com.
So
it could produce oil. They could produce pharmaceuticals.
Our civilization is totally dependent on technology.
Right.
And we can't go back. And our finite resources that we are dependent on,
I think we accept that now,
are running out.
Yep,
we need something new.
Yep.
And this is the only thing that can scale up to meet these challenges. We need this technology. And not just for that. In my demonstration, I talk about, what about glowing trees? That's not hard. You can take the 5 enzymes you need from fireflies and moving into trees, make glowing trees. What about that? That's a biological application that you would love to have.
Cheaper than street lamps.
Cheaper than street, yeah.
So what's happening here is people who are watching this are watching what is going to be a massive transformation in society and in everything. And this is kind of the beginning of it. What's really interesting is this has been in the realm of very well-funded research facilities. Yeah. You're now making this possible for less well-endowed people.
What we are doing, we are calling it to democratize.
You're democratizing
the tools of creation.
Exactly.
And quite literally creation, not just content creation, but creation itself. And yes, this is what we're trying to do, to abstract biology, make it easier, simpler, so more people can come into this field and start doing cool things with biology.
What if? But you notice that I immediately go to, oh my God, this is horrible, and I think this is not unusual reaction. Yeah. That's going to be one of the challenge. Probably maybe the biggest challenge for you guys is people are going to say, wait a minute, we don't want that. We don't want it democratized. It's not safe. How do you respond to that? Because I mean, really, that is going to be. I can see people. I know I'm being negative, Rudy.
Yeah.
Rudy in the chat room says, Leo's so negative. But that is what people are going to, how people react, I think.
So there is 2 answers that I usually give. The answer that, first of all, it's evolution, right? We're creating, this is what nature does. It creates new things. And
but now it's humans doing it instead of nature.
We're a part of nature. And,
I guess we are.
Again, everything alive has been evolved for 4 billion years of evolution to
it just
do
took
exactly
a really long time
everything
before.
That human developed, from Chihuahua, to corn, cannot survive without massive human intervention.
Right.
So anything that we'll create, I believe, and just bring to nature, it will, I think, die out from natural selection. Or to revert it to... Bacteria doesn't want to produce biofuels. They want to grow and do their own stuff. So
this is going to be a hard thing to do.
Yeah, it's a hard thing that we make them do.
Right.
They will revert to their natural state.
How far off are we from... I mean, this is going to speed things up considerably, isn't it?
Yes.
You have to have actual design tools, and a lot of the people we included in our company are people with computational type experience that can actually use the capacity. Because when you're talking about going from only being able to make 1,000-letter thing to being able to make millions of million-letter things, that type of capacity
you need requires, to make factories.
You're right. You need and you also need computational design to be able to use. To be able to explore the whole space. So yeah, you're talking about on a practical level. Yeah, you're talking about advances in our ability to produce things. On the medical side, you're going to have a real kind of fundamental shift in the way that people make biologics, people that make drugs. like when you can only make it one way, it's very expensive, and you have to have $30 million and a huge team. But when you can make these large libraries, from a few individuals, it becomes more of like an internet startup. You have.
Will we see hackers, biological hackers, in the same way we see code hackers?
If you go to genomecompiler.com, our website, and go to the news section, we have one of the videos we present there is a guy that hacked his own yogurt to produce Prozac. So he hacked the bacteria that produce yogurt to produce something else, and he did it using.
And it works?
Yeah, he demonstrated something else, producing beta-carotenoid, or the orange color that you get from carrots, into his yogurt. So you can start doing it with household appliances. So we're getting there.
Okay, so what does the Cambrian genomics thing look like? Is there an actual thing yet?
It is actually, if you want to visit, it's at 665 3rd Street.
It's in San Francisco.
Downtown San Francisco, right next to Giants
giant
Stadium.
vat? What is it?
It is a laser.
It's a laser.
It is a laser.
How to DNA hack yogurt into Prozac.
Start with beta carotene. We want to go too far, but I guess beta carotene's close enough that if you get that far, you could do Prozac.
Well, it's chemistry, right?
It's just if you could synthesize one thing. Right.
But yeah, it is.
Are you guys taking investors?
Yeah, we have.
We have more than 2 million.
Because I'd like to invest. Holy cow! I would give you every penny I have. This is a revolution.
We got investment, a few $1 million from Autodesk. They build design tools for dead matters, and they want to get into design tools into living matters.
And I'm not really allowed to talk. I'm not allowed to talk right now.
And the federal government's obviously invested in you heavily.
Yeah.
Wow.
We are meeting DARPA on Tuesday.
Wow.
So that is the military.
Unbelievable.
DARPA has a new initiative called Living Foundries.
Living Foundries.
Yeah.
Alicia Jackson's a program manager.
So can your Cambrian genomics maker bot make one bacterium? Can it actually make a bacterium?
So what we are doing is exactly like you said earlier. When people order, like Omri gives us a long sequence of DNA, we break that up into smaller pieces.
Yeah.
Okay, and so we make about 100 letters at a time, and then we assemble those into longer pieces. So at this point,
so you're just making strings of DNA at this point.
What we're doing is we're making the 100-letter pieces. The next step will be to take those 100-letter pieces and string them into longer pieces using robotics.
But there's a big gap between making the DNA and making the cells. Are you
there isn't.
It's not? Because once you have the DNA, they'll make themselves?
Yes, because the
DNA
is simply, it is software. It's simply memory. And the memory actually, like Omri said earlier, will make the hardware. So when
you inject it into a cell?
Into a cell, it will actually boot up, and it isn't the operating system.
And the cell runs it and makes more.
And the cell, you actually can put it into a different species. You can take the DNA out of one species, put different DNA, and it will actually boot up as the species that the code defines.
People are doing this already.
This is happening. Craig Venter already did that in October of 2010.
Right. 2 years ago. The issue was that, again,
just too hard and expensive.
Over $1 million for just the DNA.
So it's well known, in fact, how to create this. It's creating the software, the operating system.
If you guys read the New York Times a few days ago, Craig is working this summer on making 2 more bugs. These are minimal genomes, so the minimal amount of DNA necessary to build up an organism. It's a scientific type of project. The issue is that Craig calls these Hail Mary genomes because he doesn't know if these are going to work. He's only making 2 of them.
Right.
And
you need to make
thousands to millions because there's no feedback cycle. We can design things and do nice computational stuff, but we can't actually run the experiment.
Wow.
At the point where we can do feedback, we can actually integrate design that Omri is setting up with the actual
and debuggers and all this stuff. You're going to need a whole tool set.
Debuggers, IOs, all these.
You need a whole tool set.
Exactly.
Yeah. We're in biology is the same place we were in computer science 30 years ago.
Right.
We're just starting, and it's
except that I think it'll go very fast.
It's going to go.
I think it's going to go faster.
I mean, if you look at sequencing,
we're not talking 30 years. We're talking how long?
Sequencing went from $1 billion to $1,000.
We saw the graph like
in a few years. Yeah. I mean,
much faster than anybody thought it would.
Way faster.
Way faster.
And that was Craig Venter's kind of surprise.
Yeah. And the issue is that people realize what sequencing was because of that.
Right.
But what people don't know yet, and people don't really know something until they actually see it with themselves, which is why I'm welcoming you to come down, is that there's a new sort of paradigm which is next generation synthesis. the writing, not just the reading, but the writing, and going from millions of dollars for making an organism to a few dollars for making organisms.
That's crucial because you can design it, or you can at least.
This makes it easy to design.
Yeah, but unless you can build it, you can only make small stuff like small genetic construct. And you know what? Small genetic constructs are also important.
But you can
think about viruses are just a few thousand letters. You know, Genentech, a huge company, started with a very small construct that said overexpression of human insulin in bacteria.
To give you some
that's just
to give you some kind of idea of the economic potential here. Genentech made how many billions of dollars off of 300 letters of DNA code?
Right.
It's very valuable.
Where would you like to go first if you were going to choose the first few things that we would do?
This is a popular.
I'm actually it's pretty funny. So I in the Solve4X video I showed like our vision to the future where you can just search for let's say trees, drag an oak tree and drag the application from fireflies to make it glow. And I got a lot of positive feedback and they say, why not do it? Because it's not that hard. It's 5 genes. I actually can show it in the software. I actually have the plasmid for those 5 genes. Why not do it? So I'm going to start a Kickstarter project to do a glowing tree. And if somebody will give us more than $10,000, we'll write his name in the genome.
What?
So
actually,
I'll give you 10,000 right now.
Have you put this up?
Not yet. I'm just designing it.
We think we have someone that can actually do this for us.
So I'll do the
I don't
design
think you're going to have any trouble getting somebody to give you $10,000 right now, like write you a check. So you make a glowing oak tree.
Yeah.
Are
they're going to die easily? I mean, are they going to be, or you think they're just going to be viable?
I think they're going to be beautiful. I think that once you see them, you see that they are meant to be. I think it's like people were afraid of babies that weren't,
guys, I've been watching technology for 30 years, and I do remember some turning points. I remember the first time I got on the internet, but they've never had an experience that I'm having right now of just the floor dropping out from under me. I mean,
Well, you're talking about basically everything on the planet changing.
A revolution.
Yeah.
And I have been saying for a long time that the next big revolution, Bill Gates was saying this 20 years ago, the next big revolution from informatics to bioinformatics, this is it.
The way I like to say it, they used to say that the advanced technology is indistinguishable from magic. But now I say that advanced enough technology is indistinguishable from nature. Nature is technology. It's the most advanced technology we have on Earth.
That's right.
And we're just starting to learn how to manipulate and build it ourselves.
Yeah. It's fun to think about making bacteria as factories, both for this planet and for other planets.
Maybe do it on another planet because I'm a little worried.
And that might be a good idea.
It might get loose. Right? Let's do it on the moon.
Yeah.
Let's do it far away first. Maybe put it on an asteroid. Yeah. Will we ever have glowing babies? So you could.
Well, that's my first biological experiment. I can say.
Yeah. Are you having a glowing baby?
No, I have a baby.
How does your wife feel about that?
I have a regular baby, and
you didn't make it a glowing one, huh?
Yeah, I'm not just trying to make a glowing one, but
we're talking. I had no idea, Omri. When I saw your talk, but I didn't get it. And actually, as you say, Austen is providing.
That's my first biological application.
And she does glow, actually. Very beautiful. Yeah. That is a beautiful baby. Boy or girl?
Boy.
And his name?
Shalev. It's peaceful in Hebrew.
Peaceful.
Which means that he's very naughty and like to.
Yeah, of course. You name a kid Peaceful, what are you going to get? I ask you. You should have named him Helgen.
Yeah.
Omri Drory. You could find out more. I guess should people go to genomecompiler.com?
Genomecompiler.com, and tonight at 6:30 at BioCurious in the Bay Area and downtown San Jose, we're going to give a talk and demonstrate our software.
And BioCurious is kind of like a maker space for this stuff? For biology.
Yeah. GenSpace in New York and BioCurious in
I don't even know what to say.
Join the revolution.
Wow. Austen Heinz is with Cambrian Genomics, CambrianGenomics.com on 3rd Street in San Francisco.
Right.
Can anybody come by?
Anybody can come by. I'll show you what the laser.
Look at the vat and the laser and the thing and the holy cow. We should save this recording because I think in 10 years we might look back and say, you know what? There was something happening there. I feel like this is when, you're talking to Mark Andreessen about this browser thing might go somewhere.
And I encourage people who want to learn more also to go to wesolve4x.com. That's the Solve4X.
Lecture. Yeah.
There's lectures, my lectures, and a bunch of very interesting lectures there about different subjects.
Let's make this a TWiT special. Can we do that? Okay, thank you. We'll give it to you for a download. I mean, I think we just scratched the surface, but I think that you get it. I think we have a smart audience that kind of gets what this could mean. Pretty remarkable. Thank you,
Yeah,
guys.
and I have to say one thing. I lived during my postdoc at Stanford. I lived in Berkeley. My wife did a postdoc in Berkeley, and I drove every day from Stanford to Berkeley. And I listened to your podcast. And later, when I started my company, I came back to Stanford. And I told the other postdoc that I learned more out of driving and listening to podcasts and technology and science than working in the lab for 4 years and not getting anywhere.
Well, that's the state of biology right now. So.
Yeah.
Well, I think you guys are about to set biology on its head. In many of those, Craig kind of did it himself in a little bit.
Yeah.
You know, it was a race between the federal project and Craig Ventnor, and he blew the socks off of the federal project to sequence the human genome. And that wasn't that long ago. That was, 10, 15 years ago.
Yeah.
In 10, 15 years, I have no idea. Glowing trees, that ain't nothing.
No, that's the surface.
That's
I mean, but I think you should do the Kickstarter. And I think when people see glowing trees, I just have to caution you that the initial knee-jerk reaction is going to be shut it down.
Yeah.
You know that, right?
That's a problem. I think that's more dangerous than kids trying to make Ebola, because this is a needed technology.
This is like stem cell research. It's going to really trigger a huge culture war. And you know, that's the only thing.
Whose side are you on?
I don't know. I'll be honest. I mean, I'm on the side of science, but at the same time, this is a little scary.
I mean, we have a software engineer, and I know Omri does as well, that are actually looking purely at evaluating sequences. All the sequences are out there actually on the internet
right now.
Right, which means that when people order things, we can easily screen if there's something bad in it. Right now, humans don't have the capability of making very bad things that just come out of their head, because they're all stolen from nature.
Right. Yeah.
So if they use something that's from nature, we'll see it in the code.
I think a lot of this comes from science fiction and this thing of, Dr. Moreau's island of animals that are, took a horse's head and put it on a goat. And,
the For-Us monkey from South Park.
Exactly. And I think so. I think that's part of it, is that we don't really have a way of grokking this. It's just too it's magic.
No, it's not magic. If you just need to understand, it's nothing more than software. It's beautiful. We love it.
But look at all the trouble software has gotten us into.
Software is eating the world, and software is making. Without software, you didn't have a job.
No, it's changing the world. No, I agree.
So.
Oh my God, this is exciting. I wish you luck, guys. And I tell you, if I had $1 million to invest, I would do it right now. And you guys, because
we're doing all right.
I think you don't need my money. I think I need your money. I think you guys are really changing the world. That is very exciting.
Thank you very much.
Wow, I want to know more. And it's so nice to talk to you. And let's continue to talk. You guys are local. Yeah, we'll do more on this. I think this is very, very interesting.
I need to actually now have some ads here, because I buy everything you sell. I have an Audible account, and my website is on Squarespace. So I actually saw the jump when you mentioned us.
Thank you. You're amazing. I really am thrilled to know both of you. And what you are doing is about to change everything. And are there other people doing this, or is this? This must be something that's happening in the world, right? It's like. Or is this just a little pocket of revolution?
Well,
so Joel Church from Harvard is one of the big people. Drew Andrew from Stanford. There's a bunch of people. There is.
But I bet you the institutional people do not want to democratize it.
Well, there's issues. I mean, like with Craig, for instance.
He wants to patent it.
Yeah. Well, I met with the whole team down at Synthetic Genomics, and
they want to own it.
Well, there's issues, like Omri said. We're kind of unleashing the engines of creation democratically.
Whoops.
And there are some certain people right now that have sort of a right to make genomes, and that's because they have the money.
They patented it, yeah.
Well, because they also have. It's more actually a matter of cost.
Finance, okay.
So
you're going to bring that cost way down.
Once the cost is low enough, right?
Wow.
And we're just the printer, and Omri is making the software.
But we need the creators to actually come and do stuff.
So if somebody, a young person, and there are many watching, says, "I think this is the future," and I've thought this for years. I'm just waiting for this to happen. I knew this would happen. I'm just waiting for this to happen. How do they participate in this revolution? What should they be studying? Biotech? What should they be doing?
They should be studying, I would say, computer science.
Computer science.
Math.
More computer science.
To design things in life, it's different than designing things in software. You need to know the biology to really do something useful.
So you need biology and
software. You need
software.
biology and you need software. You need to have imagination, because in the end you're just limited by our imagination.
Well, the people who are watching have lots of imagination. I know that. Thank you, guys. It's really nice to meet you. Yeah. Wow. And we will make this a TWiT special, so we'll turn it into a special that you can download so you can tell your friends, I just saw the future, and get ready, because it's just a matter of years. That's all. Did we bring your website down? You should get on Squarespace, Austen.
Okay.
Yeah.
I think we.
Yeah. Well, I'm on Squarespace and actually see how many people just logged in. So yeah, thank you very much.
A little spike there. Yeah.
Yeah.
Wow. I think open source is better. And I think Dr. Mom makes a point, which is you need to study ethics, moral philosophy. You need to think about this, and I think also make tools so that you can analyze how things. We do need some tools. We can't just go and do it.
Sure.
But I think you're right. I think this is
and
just
George
nature.
Church, one of our co-founders at Harvard University, professor, has met with Congress to talk to them about these issues.
Because
So you got to have that side of things.
You got to do that because they're going to just go crazy when they finally figure out. I think the truth is they ain't going to figure it out until it actually happens.
Yeah, well, it's hard to make people understand what we're doing.
George's first application is a woolly mammoth. I mean, if you
I remember that. I remember actually reading about that. I like the glowing trees.